For my final project, I'm going to look at the control system for a residential heat pump. A residential heat pump utilizes a refrigeration cycle but reversed to heat a house. So the outdoor coil is going to absorb heat from outside and then transfer it to the house. Sensors for this situation would be a thermostat to get temperature, a humidistat if we were concerned with moisture in the room and we were doing air conditioning, and then a mass flow meter to record mass flow rate. This will come in handy with the example I'm going to show later. Actuators for the system would be a compressor, a blower fan, a water loop circulation pump, a thermostatic expansion valve, and a reversing valve if we were doing air conditioning. Good performance for the system would be that we are keeping the house at a desired set temperature point and not deviating from it too much, and then also being efficient and not using too much energy. Traditionally, a bang-bang controller would be used in this situation. A bang-bang controller is a feedback-based controller that abruptly switches between two states. We're going to try to implement a PID to control the mass flow rate of refrigerant to keep the house at that desired set temperature point. A PID is a closed-loop controller that processes the error of a system using proportional, integral, and derivative gains to achieve optimal performance. Incorporating this PID will cut down on temperature swings seen with a bang-bang controller, and the system will have more efficient operation. If we were to derive a system model of a heat pump, we could use system identification to derive this model. We would need to record things like input power to the compressor or ambient temperature. We could also do something like we did with the mass spring system, and we could derive a transfer function from energy balance equations or laws of thermodynamics. To tune the PID, we can use the Ziegler-Nichols self-oscillation method. This is commonly used in industry. We're going to set the derivative and integral to 0 and increase the proportional gain until the system oscillates. Then we can use that critical gain from the oscillations and use this table to find values for our PID. I'm not really concerned with response time, as it's going to take a while for a room to heat up, so we don't really need our response time to be within seconds. I'm more concerned with abrupt changes in temperature, as this may cause an offset, as we already tuned the PID for a certain situation. And I'm concerned with steady state error, as we don't want the system to stray from that set point temperature. We want it to stay on that set point. MathWorks has an excellent example for a residential air source heat pump. This heat pump is taking heat from the outside and transferring it into a water loop off of the condenser, and there's hot water radiators heating the house. In this example, there's all the components that we're looking for: a circulation pump, thermostatic expansion valve, compressor. And a PI controller is used to modulate the refrigerant in that refrigeration cycle to keep the average air temperature of the home at about 23 degrees C, as the outside temperature is modulating about between 10 degrees. If we take a closer look at the controller from this example, this is actually a PI controller, and it's commonly used in industry. We don't really need derivative, as we're not super worried about abrupt changes or noisy signals with the temperature from a house, so the derivative is not super necessary. And you can see here there's the input temperature and the error temperature from the thermostat. The controller works really well, actually. You can see that outdoor temperature modulating, and the indoor temperature has great steady state error. There's not a big percent overshoot, and it has really quick response time as well. You can see some modulation between different parts of the house, but overall it's keeping at that desired set point. The coefficient of performance of the compressor is modulating a bit, but it's staying about 2.5 to 2.8, which is average for a heat pump. And also in this graph, you can see the refrigerant modulating, and that's what the PI controller is doing to keep the house at a desired set point. Mostly concerned with the system with environmental concerns. An HVAC system in a household will use approximately half of the total energy consumed, which is quite a lot, and so we want to conserve this energy and keep a low coefficient of performance. Troubleshooting for the system mostly is tuning that PID as well as we can so that we get efficient operation and we keep that desired set temperature point. The problem we run into here is that the PID controller is more difficult to tune than that traditional bang bang controller that's mostly seen in houses, and it can possibly be more expensive. I'm not really concerned with automation, as this really wouldn't cause job loss. Thank you for listening, and these are my references.